Hi, this is the Science Chef. In this video, I'm going to teach you how to write the electronic configuration of the first 20 elements using the quantum numbers or spdf notation and its relationship with the periodic table. In our tutorial on how to write the electronic configuration of the first 20 elements using the KLMN notation, we learned that electronic configuration is simply the arrangement of electrons in an atom. We also learned that the maximum number of electrons that can be accommodated in a given shell or energy level of an atom is given by the formula 2n squared, where n is the shell number or the main energy level. In our tutorial on quantum numbers, we learned about the different orbitals present in a particular energy level, the maximum number of electrons that a given orbital can hold, the rules guiding the filling of electrons into orbitals, and the order in which electrons are filled into orbitals. Using this knowledge, we are going to write the electronic configuration of the first 20 elements by following the order 1s, 2s, 2p, 3s, 3p, and 4s, starting with hydrogen. Hydrogen has one electron, which will occupy the only orbital in the first shell, that is, the 1s orbital. This gives it an electronic configuration of 1s1. Helium with 2 electrons has an electronic configuration of 1s2. This is because the s orbital can hold a maximum of 2 electrons. Therefore, the second electron of helium will complete the 1s orbital in a downward spin in obedience to the Pauli exclusion principle. The third electron will move to the next orbital, which is 2s, according to the Orbitals principle, which gives lithium with 3 electrons an electronic configuration of 1s2, 2s1. Just like helium, the fourth electron in beryllium with atomic number 4 moves in to complete the 2s orbital with an opposite spin in obedience to the Pauli exclusion principle, thereby giving beryllium an electronic configuration of 1s2, 2s2. Now the 2s orbital has been completely filled. The next electron will move to the 2p orbital, which is why boron has an electronic configuration of 1s2, 2s2, and 2px1. Carbon with 6 electrons has a configuration of 1s2, 2s2, 2px1, 2py1, or simply 1s2, 2s2, 2p2. This is because the p orbitals are degenerate orbitals, and according to Hund's rule, electrons will fill singly first before pairing takes place. Therefore, the 7th electron in nitrogen goes into the vacant 2p orbital, giving it an electronic configuration of 1s2, 2s2, 2px1, 2py1, 2pz1, or simply 1s2, 2s2, 2p3. Having completed the single occupancy of the degenerate 2p orbitals, the 8th electron in oxygen will pair up with any of the already existing single electrons but in an opposite spin in obedience to the Pauli exclusion principle, thereby giving oxygen an electronic configuration of 1s2, 2s2, 2px2, 2py1, 2pz1, or simply 1s2, 2s2, 2p4. So this same explanation suffices for fluorine and neon with the electronic configurations 1s2, 2s2, 2px2, 2py2, 2pz1, and 1s2, 2s2, 2px2, 2py2, 2pz2, respectively. So having completely filled the 2p orbital, the next orbital to be filled will be the 3s orbital according to Orbitals principle. This makes sodium and magnesium with 11 and 12 electrons to have the electronic configuration of 1s2, 2s2, 2p6, 3s1, and 1s2, 2s2, 2p6, 3s2, respectively. The filling of the 3p orbitals from aluminium to argon follows the same pattern and explanations for the filling of the 2p orbitals. Hence, the electronic configurations of aluminium to argon are as follows. After argon, the next pair of electrons move into the 4s orbital instead of the 3d orbital. This is because the 4s orbital has a lower energy level than the 3d orbitals, according to the Orbitals principle. Therefore, the electronic configurations of potassium and calcium are 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, respectively. This principle also throws more light on why the KLMN notations of the electronic configurations of these two elements are 2881 and 2882 instead of 289 and 2810. You would really need to watch our last tutorial on quantum numbers after this tutorial to have a good understanding of what we are discussing. If you take a closer look at the electronic configurations of helium, neon, and argon, you will observe that they have completely filled p orbitals, apart from helium, which has no p orbital. They also end the filling of the p orbitals in each energy level, after which the next electron moves to a new energy level and not just a new orbital. In other words, the electronic configurations of these elements officially, in quotes, end the electron filling of a particular energy level and confers a form of stability on the elements. Any subsequent electron filling into those energy levels will be considered to be carried out through the back door, in quotes. As such, orbitals like the d and f orbitals are considered to be inner shell orbitals. So now that we know how to write the electronic configurations of the first 20 elements using the quantum numbers, let's now see how we can use their electronic configuration to predict their positions in the periodic table. From the spdf notation, the sum of the indices in a given electronic configuration represents the total number of electrons in an atom. The highest principal quantum number in the electronic configuration represents the number of shells present in the atom of an element and the period to which the element belongs in the periodic table. The sum of the indices in the orbitals with the highest principal quantum number in the electronic configuration represents the valence electrons in the atom of the element and the group to which the element belongs, while the outermost or last orbital in the electron configuration represents the block in the periodic table to which that element belongs. So for the first 20 elements, hydrogen with an electronic configuration of 1s1 is an s-block element located in group 1 and period 1. Similarly, lithium, which has 3 electrons with electronic configuration 1s2, 2s1, is another s-block and group 1 element found in period 2. Beryllium with 1s2, 2s2 is also an s-block element of group 2, period 2. While boron is a p-block element that belongs to group 3, period 2, because its outermost orbital is the p orbital and its valence electrons are found in the 2s and 2p orbitals. Carbon with an electronic configuration 1s2, 2s2, 2p2 is a p-block element located in group 2 and period 4. This trend continues for other p-block elements from nitrogen in group 5 to neon in group 8. Sodium, whose valence electron is found in the 3s orbital, is an s-block element located in group 1 and period 3. While magnesium is a period 3 and s-block element located in group 2 because its 2 valence electrons are found in the 3s orbital. Aluminium to argon are p-block elements that all belong to period 3 because the highest quantum number in the electronic configuration is 3. However, they belong to different groups because they have different valence electrons, which is the sums of the indices in the orbitals in their third shell. So for aluminium, it is group 3, obtained from 3s2 and 3p1. Silicon is in group 4, obtained from 3s2 and 3p2. Phosphorus in group 5 has its valence electrons as 3s2 and 3p3. Sulfur in group 6 has its valence electrons as 3s2, 3p4. While chlorine, which has its valence electrons as 3s2 and 3p5, is in group 7, and argon with a valence orbital configuration of 3s2, 3p6 is in group 8. Potassium and calcium both belong to the s block and period 4 because their valence electrons are in the 4s orbital, while potassium is located in group 1 of period 4 because it has 1 electron in the 4s orbital. Calcium is found in group 2 because it has 2 electrons in the 4s orbital. Helium, which we intentionally skipped, ought to be placed in the s block because of its electronic configuration 1s2, but it is usually found in group 8, which is the p block. This is because the 1s orbital is the only orbital in the first shell or energy level, and the second electron of helium is used to complete the filling of that energy level. Any element whose electronic configuration, officially in quote, completes the orbital filling of a given energy level is known as a noble gas and is usually placed in group 8 or 0. You can now click on the link showing on the top right corner of your screen to watch our tutorial on quantum numbers. If you learned anything from this video, drop a comment, encourage us to do more by giving us a like and subscribing to our channel. Don't forget to always turn on your notification bell to stay updated with new uploads. A wise man once said, "The present time is a raw material for your future success if judiciously used." So always make judicious use of your time till I see you when I'll see you.